Welcome to part 2 of chapter number 8. We're going to continue our look into the electrons. We talked about them being waves and acting like waves, just like light. Well, okay, we talked about light acting like a wave in the last part. We are now going to talk about light acting as a particle, and then we're going to start talking about electrons and how we can combine the two. And actually, what we see here is light behaves as a particle. This is known as the photoelectric effect. Depending on the wavelength of light, there might be enough energy in that light to remove an electron from a metal, right? We talked about how metals like to give up their electrons. They can relatively easily give up their electrons. We'll talk more about this in chapter number 9, I believe, if not 9, 10 then. And so what we can do is we can actually have a current just by light, right? Having light intensity hitting it, bringing off an electron. Now, the photon, the particle of light, we'll talk about what that is. But the particle of light is what plants actually use, right? That they use that behavior of light when they do photosynthesis to make sugars from CO2 and water. Now, we can calculate the energy of each photon. And what a photon is just a packet. You can think of it as a packet of energy, right? A packet of light. It is just a small little thing of light. Now, what we're going to see is a photon is very small compared to the whole, and where light gets the majority of its energy as having a bunch of photons versus just one individual photon. And so this was first suggested by a guy by the name of Max Planck. It was expounded on by Einstein. Now, the energy of a photon, we're going to see, is directly proportional to its frequency, right? This is why we said gamma radiation has a higher energy than does, let's say, infrared radiation, right? And that's because it is a higher frequency, right? And if it's directly proportional to frequency, then it's inversely proportional to its wavelength, right? And we see that in the relationship between frequency and wavelength. And so how can we calculate the energy of, well, that was interesting. How can we calculate the energy of a photon? I'm glad you guys asked. So what we see here on the board is we see a few equations, and I'll try to carefully, because it's kind of blurry, walk you through what's on the board here. So the very top one is the equation for the energy of a photon. Now, the energy, remember, is in joules, but the energy is equal to H. We said this was described by Max Planck, and so of course he has a constant named after him. This is known as Planck's constant. It is 6.626 times 10 to the negative 34th joules times seconds. Again, you will be given this constant on an exam or on the quiz. And then times frequency. We said the energy is directly proportional to frequency. Frequency we know as in inverse seconds. So then when you do this calculation with frequency, your seconds cancel out, leaving you with joules, which is the unit of energy. Notice that Planck's constant is very, 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 very small. When we calculate the energy of a photon, we're calculating the energy for one single photon. One single photon does not have a lot of energy. But a lot of photons have a lot of energy. And so then what we can do is we can think about this for a second, to where we said energy is equal to Planck's constant times frequency. Well, we know from part 1 that frequency is equal to the speed of light divided by the wavelength, right? There's that inverse relationship. And we just said that the energy of a photon is inversely related to, or inversely proportional to, its wavelength. And so what we can do is we can solve that frequency equation. We have the frequency is equal to the speed of light divided by wavelength. We know that wavelength is equal to the speed of light divided by frequency, right? And so what we do is we solve it for the frequency. Then what we can do is we can plug in that equation. We can plug in this equation, C divided by wavelength. We can plug it back up into here, into this frequency, And now we have this new equation. Energy is equal to H times C, which is a constant, right? Constant. 3.00 times 10 to the 8th is the speed of light. And then you have Planck's constant, which is written there on the board, divided by the wavelength, right? This is for a one light photon, right? So if you're given a frequency, you can use the top equation. If you're given a wavelength, you can use the bottom equation to calculate how much energy is contained within that photon. And so let's go ahead and switch cameras. Let's go back to the PowerPoint, right? And so we can calculate the energy of a photon. Now, what we're going to start to do, right? Because we said this is light, and that's great for light, but we want to really talk about electrons, right? We want to talk about electrons. And so what we can do is atomic spectroscopy studies the electromagnetic radiation absorbed and emitted by different atoms. And so what happens is you can excite electrons using electricity, or in the case of the lab that we'll be doing, fire. And then what happens is those electrons get excited, they relax, and when they relax, they emit wavelengths. They emit wavelengths of light. And what you can do, it results in a series of bright lines. These are known as emission spectrums. What you can see is in the little example picture there on the PowerPoint, you can see white light spectrum, right? It's all from purple to red. And then for barium, you get a nice different colors of spectra, and for helium, you get a different spectra, right? Because there's different electrons. We'll talk about electrons and where they are in a little bit more detail in chapter number 9. But for this case, just know that they're different. They're different levels. Each one is unique. This is the photoelectric effect. Now, why do we use this, right? What we use this in real life. Can you guys think of an example where we would use these spectrums, right? That these different elements give off different lights? In neon lights, exactly. We can use them, neon and argon and all those different noble gases can have different colors. What else? Fireworks. That's the one I like, fireworks, right? So different metals give off different colors, and that's actually where we get the colors for fireworks, is we utilize these spectrum, and we excite them using heat, using fire, and we get nice colors in the end. Physics, though, when we try to explain, when scientists try to explain why they see these different spectra, physics cannot explain it. And so what happened was this guy named Niels Bohr comes along, and he made a model to explain the different spectra of atoms, right? And he says, well, here, there's electrons in these different concentric circles. We'll talk about what those circles are in a minute. That they're inhabiting these different spaces. And when they get electrified, when they get energized, they move to a higher energy level. And when they relax, they emit these wavelengths. I will teach you guys maybe how we can calculate the wavelength of an electron, again, in a couple slides. And so Bohr comes along and says, hey, this is how we do it. Now, what's interesting, right, and this is where we kind of have to start to think and wrap our mind around electrons, is electrons have a wave particle, right? That here we just said they emit wavelengths. They emit wavelengths when they go from a higher energy level to a low energy level. However, they do not interfere with each other, but they do interfere with themselves. And we're not going to really focus on this per se. Shows the wave nature of the electron is an inherent property, right? Each individual electron has its own. But alongside with that wave, we also have a particle, right? It is a particle. Electron is a particle as well as a wave. And again, it's something that we're going to have to conceptually try to think about, I guess. But we can calculate the wavelength of a single electron traveling through space. Now, how might we go doing that? The wavelength is related to, obviously, its kinetic energy, right? How much energy does that electron have will influence its wavelength. This is known as the de Broglie relationship. And we're going to see Planck's constant coming back into this equation. So let's go ahead and look at the equation. we're not going to be doing a lot of just the calculations, the manipulations in these lectures. But I have given you guys a good amount of practice problems with these different concepts. And so as you are going through them, if you are finding it, just like me, Dr. Bishop, I'm just having a difficulty manipulating this equation, please let me know. And we'll take care of it. So we have wavelength is equal to Planck's constant. So Planck's, and that is again 6.626 times 10 to the negative 34th. I'm going to write it joules for now, divided by mass and this is a velocity, right? And velocity is in meters per second. And I'll show you why in a minute. This mass is actually in kilograms. And so now you're looking at this equation and you're thinking, well, wait a minute, how in the world does this work? I don't understand this. That Planck's constant divided by mass times velocity. How in the world is, none of these things are going to cancel out. And so this is where I told you guys we're going to have to remember this from the previous chapter, I believe we talked about kinetic energy in chapter number 7, right? And I said, hey, remember, kinetic energy or joules is equal to 1/2 mass velocity squared, right? And we said joules is going to equal kilograms times meters squared divided by seconds squared. Right, and what we can say, and so when we do this and we calculate all of this stuff out, I believe there's an extra second over here. When we calculate all this stuff out, what we get is we are left with meters, right? And we said if we're given a wavelength that's left in meters, we have to convert it to nanometers, right? But just to show you, right, we have to think of a new definition of our joules unit so that this can work, so that we can cancel everything out. Just to let you know, the mass of an electron is 9.11 times 10 to the negative 31st kilograms. Now again, on an exam or on a quiz, if I were to ask you to calculate the wavelength of an electron traveling at this speed, traveling at this velocity, what is its wavelength? I will give you guys the weight, the mass of an electron in kilograms. Oh wow, you really can't see that equation because of the light. So it's lambda equals h. That's a little better. H divided by m v, which is for velocity. And so just keep that in mind, but we can use this actually, and what you'll find is we can use this equation to really calculate the mass of anything that we wanted to. So if we wanted to calculate the mass of a basketball traveling at a specific velocity, we could calculate we could use its mass, we could calculate its wavelength. Now, obviously that's a little bit, obviously the basketball is not behaving like a wave, but we could still do it. It's hard though, right? And this is one of the things that we're going to start talking about as we get into the final portions of this chapter. Is it's really kind of hard to reconcile the particle nature of an electron, right? I'm leaving the board up just so you guys know, because I will go back to it. Actually, I'll just switch the cameras because in a couple slides we'll go back to the board briefly. And so these are known as complementary properties, right? They exclude one another. So the more that we know about the wave nature of an electron, the less we actually know about the particle. The more we know about the particle, the less we know about the wave. Because of this, we have what's known as the Heisenberg's uncertainty principle. The more accurately we know the position of an electron, the less accurate we can know its velocity. What does that look like? I just want to show you the equation. We're not going to use it. We're not going to calculate it. But I just want to show you. This is why you never both see the interference pattern and simultaneously determine which hole the electron goes through, right? So it's really hard to see both the particle nature and the wave nature. And so what we get is this, right? This is the uncertainty principle, Heisenberg's uncertainty principle. So this is the uncertainty of the position times the mass times the uncertainty of the velocity is greater than or equal to, we talked about h, which is Planck's constant, divided by 4 pi. So what we see is this is a constant, right? That's a finite number. But what we see is that actually the more we know about one, the less we know about the other. And the more we know about the other is the less we know about the one, right? And so I just want to show you this is Heisenberg's uncertainty principle. And so he used it to say, well, hey, we really actually can't know much about these electrons, or at least the more we know about the particle nature, the less we know about the wave nature. And so what we can do is then we can make a probability distribution map, right, for the electrons in question, right? And so deterministic is that, the present determines the future. If I were to throw a baseball, we can kind of guess where it's going to go based on its trajectory, based on the wind, stuff like that. Indeterministic has the same starting spot, but and we kind of know where it's going to end up, but not really. And so what you see is you see the classic trajectory versus the quantum mechanical probability distribution map. And with regards to electrons look like the one on the right than they do on the left, right? Is again because we're uncertain. We don't know exactly where it's going, but we can predict it. So the question then is, right? Because again, we're talking about where electrons are. We're talking about how electrons behave. How can we predict where they are going? Well, that's a great question. So we're going to go back to the board one last time, at least for now, one last time, and then we'll stop part 2, and then we'll come back with part 3, and we'll start talking about things called orbitals, or the predictions of where these electrons will be around the atom. So what happens was a guy by the name of Schrodinger came up with this equation. And what this is just operators, mathematical operations that represent the total energy, both kinetic and potential energy in an electron. This is the energy of the electron. These are wave functions. We don't really need to know like how to solve this, right? But what happens is we can put that into a computer, because we put everything in a computer nowadays. But we put that equation into the computer and we solve it, and here's what we get. We get this. We get different numbers, right? We get different numbers. These are known as quantum numbers. These things are going to be very important when we talk about electrons. And so the principal quantum number N is the overall size and energy of what's known as an orbital. Orbitals, what we're going to see are the predictions where these electrons are going to be. There's going to be different sizes. There's going to be different energies of these orbitals as you go up from the electron, or from the nucleus, excuse me. Angular momentum quantum number, which is L, this is the this determines the shape of the orbital. So the N just determines the size and the energy. L determines the shape. We'll talk about the different shapes with regards to L's in part number 3. And then the magnetic quantum number, MS, corresponds to the spins. This is the same, they have the same MS usually among all electrons. We'll worry about this in the next chapter when we start to fill out these different orbitals. And so this is a way that we can predict where an electron is going to be around an atom. This ends part 2. Part number 3, we're going to dive into these numbers and into these shapes in a little bit more detail. And then we'll be done with this chapter, go on to the next chapter about actually how to place these electrons.